So this is EE698G. We are at lecture 17. So we are continuing our discussion on jitter and phase noise. And in today's class, we'll be qualitatively looking at how these jitter and phase noise is going to manifest in some of the commonly used circuits. So let's start with a CMOS inverter. Now, this discussion can easily be extended to delay lines because you cascade enough CMOS inverters, you have a delay line, right? So let's consider a CMOS inverter. Now, let's say this is its VDD, and say that this VDD has some noise on top of it. So now this is VDD plus some Vn, which is a function of time, right? And let's also assume that this Vn of t has a PST given by Svn of f. How can we calculate the relationship between Svn of f and the output phase domain PST? So the phase noise PST appearing here, how do we relate it to Svn of f? Any suggestions? So this out will have a corresponding phase associated with it, which is a function of time. And we are interested in calculating this S phi of f. Okay, right. So first step is to find the transfer function, right? So we can define a transfer function, KVDD, as dou phi out by dou VDD. So for a small change in VDD, by how much does my output phase change, right? So once we define this, what we have is this: for a small change in VDD, I can multiply this with this KVDD, and I will get a corresponding change in phi out at the output, correct? So now can you give me the expression of S phi of f? So you have the transfer function. What is the next step? Square of the transfer function. So this is now not a function of frequency. So KVDD square into Svn of f. Okay. So now if Svn of f had a white noise spectrum, right, then my S phi of f will simply be a scaled white noise spectrum. So it preserves the shape, you just have a scaling factor. Okay. So now let us consider how thermal noise is going to result in a jitter. So let's say I had an input going from 0 to VDD. Correspondingly, my output is going to go from VDD to 0. So let me exaggerate it a little bit. So this is with respect to time. This is, let's say, my V0, the output voltage. It is going to go from VDD to 0 like this. Okay. Now let's assume that during this transition, the NMOS is what is active, correct? I can model this simply as an NMOS, which is discharging a capacitor. Okay, so let's assume a load capacitor CL. So this NMOS is discharging this capacitor. So I'm going to replace it with an ideal current source. Let's say this is the average value of the NMOS current. And if this NMOS had thermal noise, I can represent it with an IN square here. So what I'm representing is basically the PST of the thermal noise current, right? If there is a confusion, I can also write it as IN. Okay, so now in the presence of this IN, how would this transition look like? So I'm interested in the transition from VDD to 0. At the point VDD by 2, this is the ideal position that we expect, right? Now in the presence of this IN, you will see that this point is now going to shift in time. Right? For example, maybe in the presence of noise, this does something like this. So now, instead of shifting at, let's say, T0, it is shifting at T1. This voltage is reaching VDD by 2 at T1. Maybe if I observe it for a different edge, it is going like this. So then this is happening at T2, etc. So this is what we called as jitter, right? If I had an ideal clock and I compared it to the threshold crossing points, this would be my absolute jitter. The difference between the ideal position and the actual value would give me the absolute jitter, right? So the presence of this IN is resulting in a jitter. This is okay. So now let me ask you another question. Let's say I cascaded some 3-4 inverters. So this is my input, O1, O2, O3, and O4. I injected a rising edge here. I will get a falling edge, another rising edge, falling edge, rising edge, etc. Now, each of these inverters are going to add its own jitter to the edge. So assume that the first input edge was very clean. Now this edge will have some jitter. That means the edge could get shifted like this. Now, can you comment on the jitter that you will see on the third edge? So corresponding to O2. So before that, let's assume that the jitter, the phase noise power, the jitter power at this edge is some sigma square J. That means it will have an RMS sigma given by square root of this. So can you comment on whether the jitter you see here will have a larger standard deviation or a smaller standard deviation? Is the question clear? It will be larger. Why? So this is assuming that the events that cause these jitter are independent of each other. For example, thermal noise. Okay. So it will be larger simply because the edge reaching here already has a jitter. On top of it, the inverter will add some more jitter. Therefore, you can expect it to increase, right? So this edge, you will see a larger standard deviation. This will see even larger standard deviation, etc. Right? So if I'm looking at the nth stage, and if each stage is adding a jitter of sigma, an RMS of sigma, how much would be the jitter present at the nth stage? So let's talk about the phase noise power or the jitter power. Okay, so if each stage individually, each inverter individually is adding a jitter power given by sigma square, right? And if all these events are uncorrelated, what would be the power at nth stage? Yeah, so that will be equal to n times sigma square, right? Therefore, the RMS jitter is going to increase by root n. So if you have n stages cascaded, and if thermal noise is what is causing the jitter, or some uncorrelated event is what is causing the jitter, then you expect to see an increase of root n as you keep cascading n stages. This is okay. So now let's also quickly look at the effect of flicker noise. So I'm going to model the flicker noise as a voltage source at the input of the PMOS. For now, we'll assume that the NMOS doesn't have any flicker noise. Okay. Now, of course, it doesn't make much sense for me to write a plus or minus sign, but humor me for a minute. It will become useful when we do some transformations on the circuit now. Okay. So let me call the circuit as A. Now I'm going to make a small change. I'm going to separate out this connection. So this is my input. This is my output. So this is in. This is also in. So A and B are equivalent. Is there any difference? They are same. Okay. So now let me do one more transformation. I'm going to shift this Vn from the gate side to the source side. So how should the signs be? So in shifting it from the gate side to the source side, we don't want any current or voltage in the network in this PMOS and NMOS transistor to be affected, right? We will also make a small assumption that the channel length modulation of the PMOS is 0, right? Which means that this Vn is now not going to cause any issues with respect to the VDS or the VSD of the PMOS transistor. So what matters is the VSG of the PMOS transistor. So to retain that as the same, I need to give these signs. Okay. So just to show you this, I have retained the signs of Vn. So from now on, it is not required. So then now I have the circuit C. So if I assume that the channel length modulation of the PMOS is negligible, then A and C are equivalent. Okay. So now that I have modeled Vn here, what quick result can you tell me? What comment can you make about S phi of f at the output? So this is equal to KVDD whole square into S Vn of f, right? So we started with flicker noise. So Svn of f is a function of frequency. So I'll write it as some constant by f. Okay. So flicker noise in the transistor is resulting in 1 by f noise, phase noise at the output. So now we will do some quick comparison between the delay line and the ring oscillator. Okay, so this is my input, this is the output. Now let's say I take the same delay line. And I make a connection like this so that it acts as a ring oscillator. Let's assume that this has a delay TD. What is the oscillation frequency? One over 5 TD. Everybody agrees? Okay. So then let's analyze this. So let's say, let me call this as 0.1 and this is 5. Right? So if there is a rising edge at N1, this rising edge is going to result in a, so 1 and 5 are same, right? So this rising edge is going to result in a falling edge at N1, correct? Now this falling edge has to again result in a rising edge. This forms one period, right? From this rising edge to this falling edge, what is the delay? This is 5 TD, right? From the falling edge here, so this falling edge to a rising edge here, what is the delay? Another 5 TD. So the time period will be equal to twice the number of inverters into the delay of each inverter. Therefore, the oscillation frequency has to be 2n times t. Okay, so now the delay line is a driven system. It is being driven by some input source, right? You have a rising edge or a falling edge at input, and the same signal is then passing through the delay line. So you need something to drive it. Whereas the ring oscillator, is it a driven system? No. So what is it called as? Oscillatory system, self-sustaining system, right? But in terms of driven, then it's called as autonomous system. Okay, so now let me look at its output. Okay, say I looked at its output for 10 minutes today. I looked at its output for 10 minutes tomorrow. Assume that the system is continuously running. What comments can you make about the power of the jitter here, or the RMS of the jitter? Does it change from today to tomorrow? The RMS has to be same, right? What would be the value of RMS? If each stage is adding a jitter of sigma j, this would be RMS. We are looking at RMS. So it will be root n times sigma j. This is assuming uncorrelated events, right? Now, let's say I do the same thing for the ring oscillator. I am observing this output. So I observe it today, tomorrow, 100 days from now. What comment can you make about its RMS? With every cycle, it is going to increase, right? So this delay line has a bounded jitter, whereas the ring oscillator has unbounded jitter. Okay, so if I were to look at the output of this ring oscillator, let's say I tap from this point. And let's assume that the first edge happened to be clean. The next edge will have some jitter, right? The edge after that, so this edge, falling edge will also have jitter. I'll just focus on the rising edges now. This is going to have more deviation in jitter. The next edge will have even more sigma, etc. So this is going to keep increasing. That is, it has an unbounded jitter. So now I have a question for you. If the jitter is unbounded, what sort of jitter definition should we use when we are going to talk about the jitter of an oscillator? Feel free to refer back to your notes. Yeah, so because absolute jitter is unbounded, we tend to quote cycle to cycle jitter for a standalone oscillator. Because the jitter, the period, if I take two adjacent periods, we don't expect the period to vary by a large quantity. Okay. Now that said, depending on the application, you may want to look at n-period jitter and other forms of jitter. So now let us also look at the effect of supply noise on the ring oscillator. Is it going to be useful? Oh, very good question. Let me actually rephrase it and ask it back to you. So if the oscillator noise is going to be, the jitter is going to be unbounded, do you think we can create any circuit reliably using an oscillator? Yeah. I mean, it is going to deviate a lot from the expected clock, right? So as with most of the problems we deal in analog circuits, there would be some solution. And usually the solution is put everything in a negative feedback. So it turns out you can design an oscillator and you can put that in a negative feedback. And then you have some, you can sort of bound the jitter of the oscillator once you do this, right? So putting this oscillator in a negative feedback, that results in a phase lock loop circuit. Okay, so this, making sure that the jitter doesn't increase in an unbounded fashion is one of the uses of the phase lock loop. There are other uses as well. Yeah. Now, also, certain types of oscillators tend to have more phase noise compared to other types of oscillators. For example, an LC oscillator is known to have lesser phase noise compared to a ring oscillator, right? So if the jitter is a concern for you, or if phase noise is a concern, you first will have to pick an oscillator architecture that inherently has lower phase noise. Then on top of it, you put it in a negative feedback. Yeah. So we will learn about oscillators in the next class. And after that, we'll see how we can put these oscillators in a negative. But very nice point. So let's say this is my supply. So the supply has some noise given by VDD plus Vn, where this Vn has some SV of f. So how do I proceed now? I want to calculate. So this is my output node. I want to calculate what is S phi of f. So to make things a little simpler now, I'm going to define my KVDD as dou omega out by dou Vn. So earlier we said that if KVDD changes, if there is a change in the supply, the phase or the delay of each inverter is going to change. If the delay of the inverter is going to change, then the oscillation frequency is going to change, right? So I'm directly defining my KVDD as dou omega out by dou Vn. The units of this KVDD and the KVDD we defined earlier will be different, right? So now what do I do? I am still interested in, let's say, S phi of f. So we first have to find out the transfer function from Vn of t. There is some transfer function that will give me phi n of t. Can you find this transfer function? So this will be equal to KVDD by S. So now can you give me the expression for S phi of f? KVDD square. This is in terms of f now. So 2 pi f the whole square into SV of f. So let me bring all the common factors, I mean, everything other than f to one side. 2 pi square into SV of f divided by f square. So now if SV of f had a white noise spectrum, your S phi of f has a 1 by f square spectrum. So initially we saw that for a delay line, if the supply voltage had a white noise spectrum, the delay line output will also have a white noise spectrum, right? But if we make this into a ring, and if the supply voltage has a white noise spectrum, the output will now have a 1 by f square spectrum. Is this clear? Number of inverters we have in the yeah. So now I have defined for this particular circuit, I have defined my KVDD. So depending on this KVDD would be a function of number of inverters in the system.
So when we're going to calculate the KVDD for then each inverter having a KVDD, then
So this is a very non-linear process, right? The supply voltage affecting a delay. So generally, how we find this KVDD is through simulation, right? So you will have a nominal VDD, then you will vary that VDD by plus or minus 5 to 10%. You will look at the plot of delay or frequency versus supply voltage. You take the derivative of it, and then around your VDD, because VDD is now your bias point, you will calculate what is the slope. So that gives you your KVDD. And this KVDD will be a function of n, but I don't want to make a statement. So I expect that it is going to be summation. It will not be multiplication. I expect it to be summation, but I don't have an exact expression for it. So next, we will look at some tutorial problems. So I'll stop the recording here.